Welcome everybody, this is unit 5.3. This is our last lesson for logs and exponentials, so naturally we have to look at some word problems. Alright, so we have a couple different types of functions that we're going to talk about for real life applications here. So the first one is non-rate exponential. So non-rate, we're going to use y equals a times b to the x. Okay, we know that a is the initial value, b is your base, okay, so your growth or decay rate, and xy is an ordered pair. So we're going to write an exponential function for, at a first concert, a band had 144 people in attendance. After 4 years, the attendance was 21,609. We're going to write an exponential function to model this situation, and then we're going to determine how many people could be expected to attend after 7 years. So you're going to need two ordered pairs, one of which is going to need to contain the initial value. Well, at their first concert, okay, that would indicate time 0, 0, 144, which is your initial value. Okay, and then we have after 4 years, there were 21,609 people in attendance. Okay, so we're going to use 4, 21,609 as our xy in y equals a times b to the x. Okay, so 21609, my initial value 144. You're going to be solving for the base, okay, and my exponent is 4 here. So in order to solve for the base, we have to get it by itself, so we're going to divide by 144, okay, and it's really important that we keep that value exact. So if that does not divide evenly or to a terminating decimal, you're going to want to leave it as a fraction. So this one happens to divide. Okay, this does terminate. And then we're going to take the fourth root here. Okay, again, make sure that you take the fourth root of that entire number. Okay, and if need be, you can round that to 4 decimal places. All right, but we get 3.5. That's nice and terminates for this one. All right, so my function, my equation here, y equals 144 times 3.5 to the x. Okay, that's my equation. So now I'm going to use that equation to determine how many people can be expected after 7 years. So remember, years was my x value. So I'm just going to plug that in. Okay, we actually get a decimal here. We get 0.875. All right, but since it's people, we're going to round down. Okay, and that's my final answer for part 2. Okay, my second type of equation here is rate. Okay, it's exponential growth or decay using rate. Okay, so it looks very similar to non-rate. Instead of having just a base, if you had 1 plus a percent increase or a percent decrease, you would be looking at the same type of setup. Okay, so you're going to be given a percentage in rate problems, and that's how you know to use this rate formula as opposed to non-rate. If you see a percent. Okay, so for growth, it's 1 plus r as the base. Okay, decay is going to be the same thing. It's going to be 1 minus r. So the first census was conducted in 1790, and at that time there were 3,929,214 people. Since then, the population has grown by approximately 2.03% annually. That's your key there, percent. So I'm doing a rate problem. Okay, and my rate comes from 2.03%, but we don't work with a percentage, we have to work with a decimal. So we're going to swoop 2 places, and we're going to be using 0.0203. Okay, your initial value, because it says the first census, gave us 3.9 million here. Okay, and we're going to plug all of that in. You could use Y. Okay, same thing. Okay, you could use T for time. X would also be appropriate. And that's it. There's no other work to be done. The only thing that I'm going to ask that you do is simplify and add together that base. Okay, so instead of 1 plus, just make it 1 point. But that is your entire equation. So rate problems are actually a lot easier than non-rate because there's no solving in order to get the equation. Now, if they then asked you to predict a future value, you'd have to do a little bit more. Okay, so like I said before, the decay for rate looks exactly the same, except now you're doing 1 minus. So you're going to have to pay attention of whether or not it's growth or decay in the problem to make sure that you use the appropriate 1 plus or 1 minus. Okay, so all of that's going to remain the same. So a cup of green tea contains 35 milligrams of caffeine. The average teen can eliminate approximately 12.5%. So again, there's a percent. That's our key. Okay. 12% of caffeine from their system per hour. Write an equation to model the situation and then estimate the amount of caffeine after 3 hours. Okay, so we have to determine if it's growth or decay. So that key word there, eliminate, that means decay. So we're going to be using 1 minus in our base. Okay, so my rate, I'm going to take that 12.5%. I'm going to convert that into a decimal. 35 milligrams is my initial value because that's what the T begins with. So 1 minus okay, and again, the only work that I really ask that you do for the equation is to simplify. Okay, so now we're going to take that equation and we're going to process after 3 hours. So 3 hours is an X value. We're going to plug that in. Okay, so after 3 hours, there's about 23.45 milligrams of caffeine remaining. Okay, so here's a really nice real-life application, and that uses compound interest, so like your savings accounts. Okay, so here's your formula. And again, all of these formulas will be given to you. You're just going to have to know, well, what is R, what is N, what does T represent? Okay, so A is the amount of money that you're going to have after T years. So A is your total. Okay, P is the principal amount, which is another word for initial. R is your interest rate. So again, that's going to be given to you as a percentage, and you're going to want to convert to a decimal. N is the number of compounding periods each year. So the problem is going to tell you how many times it's been compounded. It'll say monthly, weekly, bi-monthly, bi-weekly, quarterly. Okay, so monthly, let's maybe write some of these down. Monthly would be 12 times because there's 12 months in a year. Okay, weekly would be 52 times. There's 52 weeks in a year. Quarterly would be 4. Bi-monthly, that means every other month, so that would be 6. And bi-weekly means every other week, so that would be 26. Okay, so you have to know, based on the terminology, how many compounding periods that gives you. So an investment account pays 4.2% annual interest compounded monthly. If $2,500 is invested in the account, what will be the balance after 15 years? Okay, so it says interest compounded monthly. So monthly means that I have 12 compounding periods. My rate is 0.042. My principal is $2,500 and my T is 15. Okay, so this is just a straight shot. Plug it all in. Okay, so there's your setup. We're going to plug the whole thing into our calculator. Remembering that it's money, so we're going to round to 2 decimal places. Okay, so looking at this, we've almost nearly doubled our money because you began with $2,500 and you've got $4,600 now. So you're almost at double in about 15 years. So 4.2 is actually a really good interest rate. Okay. So a certificate of deposit pays 2% annual interest rate compounded quarterly. If you deposit $500 into the CD, how long will it take for you to have $1,500? Okay, so the 2%, that's our rate. Compounded quarterly means it's been compounded 4 times. You're depositing in $500, that's your principal. And you want to know how long it will take. So T, you don't have T, but now instead you have $1,500 as your A, your final amount. So you have a total, you have a goal that you're trying to see, well, how long is it going to take for me to reach that? So we're going to set everything up. So now the variable that you're trying to solve for is in the exponent. We're going to have to use logs. So we're going to get all of this by itself by first dividing out the initial amount. Okay, and again, if that does not divide out evenly, you have to leave it as a fraction because you need the exact amount. Okay, so let's figure out what we have inside those parentheses and if that's a nice exact amount, if it's not going to be, a repeating decimal, what do we have there? Okay, we actually have a nice amount there. Okay, I'm going to flip this equation around, okay, because I think that for your brain, you have a little bit better understanding when the exponent is on the left. I don't know why. All right, so right now I'm looking at an exponential equation that has a base of 1.005 and a base of 3. Two different bases that I'm not going to be able to get to be the same thing. So how do we handle an equation like that? We take the common log of both sides. Okay, so I have an exponential equation with two different bases. So we're going to use the common log. So we're going to bring 4t to the front. Using my properties. And now I can get the t by itself if I divide out. So other than that decimal, which I know how we feel about decimals, other than that, this looks exactly like an exponential equation that we were doing in 5.2. Okay, and we can plug that into our calculator and see, well, how many years is it going to actually take me to achieve this goal with this much money? Right, and just for, being unified all over everything, we'll just round to 4 decimal places again. All right, so the only time we'll do 2 is with money. Everything else we'll do 4, just so that we're the same across the board. So we're looking at almost 55 years. Okay, so that shows you that 2% is not a great interest rate. Okay, and not only that, but it sounded like compounding it monthly, compounding it 12 times a year, was better than only doing it 4 times a year. Okay, and the last type of problem that we want to look at is continuously compounded. Okay, so you have to be careful because there's compound interest, which is just regular compound interest, and then there's continuously compounded. So anytime that there's continuously compounded, we're using a base E. So we actually have all of the same variables that we did before. Okay, we have a principal, we have an amount after t years, and we have a rate, but now we're just using a base E. So you're looking for the keyword of continuously in these types of problems. So when Angelina was born, her grandparents deposited $3,000 into a college savings account, paying 4% interest, compounded continuously. Okay, so continuously is the key word that's going to tell us to use PERT. Okay, so the principal is $3,000. We want to know what is her balance after 10 years, and our interest rate was 4%. Okay, since E is just a number, we can plug this whole thing into our grapher, into our calculator to evaluate. Okay, so if you're using second ln, that'll bring up your E to an exponent function. Okay, so again, this is money. I'm looking at 2 decimal points. Okay, so after about 10 years, she'll have $4,475.47. Okay, so those are your 4 types of exponential word problems. So we have non-rate, rate, and then we have 2 kinds of interest. So there's compound interest and then continuously compounded. Okay, so we're going to do a lot more practice with these over the next coming days. Just make sure that your notes are complete and write down any questions that you have. All right, that's it for this time. Thank you so much for watching, guys.